So here we will consider a very simple example consisting of two particles, and we will apply the virtual work method to find out the governing equations of motion, and we will see the similarity between this virtual work method and Kane's dynamics. So this is the problem. This is a well-known problem. So this is one block. This block can be treated as a particle. This block slides over this frictionless surface, and the mass of the block is m1, and this block is fixed to the wall through a spring of stiffness K. So from the block there is a frictionless hinge, and from the hinge a massless rigid link is there, and at the end of the link there is a concentrated mass m2. So we call this block A and call this concentrated mass P. So we fix the coordinate system capital X in this direction and capital Y in this direction, and at this configuration the spring is undeformed, so the spring force is 0. Now what happens? The block starts to move, and it is a 2 degree of freedom system, so you require 2 degrees of freedom to specify the configuration of the system. So 1 degree of freedom is the location of the block along capital X, and that is q1, and other the angle from the vertical. The z direction is going inside the paper. This is X, this is Y, and the z direction is going inside the paper. So the position vector actually of this particle is RA, because this we are calling A, so this is RA. RA is a function of Q1 and Q2, and it is actually here Q1I, and RP is also a function of Q1 and Q2 in general. So this is Q1I, so Q1I minus L sine Q2 I plus L, this is L cos Q2, the vertical distance, L cos Q2 J. So now suppose on this configuration we give a virtual displacement del q1 and del q2. That means we give a virtual displacement without violating the constraints, so it moves in this direction by an infinitesimal amount del q1, and in this direction, in the increasing direction of q2, an infinitesimal rotation del q2. So this is without violating the constraints. We give a virtual displacement and it takes no time. So now the change in RA due to this change in Q1 and Q2 should be del R del Q1 plus del R del Q2 del Q2 and del RP is equal to del R. Sorry, this is del RA, this is del RP del Q1 plus del RP del Q2 del Q2. Now suppose Fa is the active force acting on A. Active force on A and Fp is the active force on P. So active force means the force which does virtual work due to the virtual displacement given. So here actually, so this spring force KQ1 does virtual work due to change in Q1, and this weight M2G, this acts on particle P, and this does virtual work. So since this block moves in this direction, the weight of this block being perpendicular to it, and the normal reaction that is also perpendicular to it, so they cannot do any virtual work due to this movement because it moves in this direction. So the active forces are the spring force, and this spring force is acting on particle A, and M2G is acting on particle P. So and now if you find out the accelerations, so inertia force acting on A is equal to minus mass of particle 1 into acceleration of A, and AP. So this is the inertia force on A, and this is the inertia force on P, and the virtual work principle says that Fa dot delta Ra plus F in A dot delta Ra plus Fp dot delta Rp plus F in P dot delta Rp is equal to the virtual work done, and that should be 0. This is the virtual work principle, that the virtual work done by the active forces and the virtual work done by the inertia forces should be 0. So this is the virtual work done by the active forces on A, virtual work done by the inertia force on A, virtual work done by the active force on P, and the virtual work done by inertia force on P. So this should be 0. So now we can, in place of del Ra, we can put what we are getting from here. So this turns out to be Fa plus F inertia A dot del Ra, and del Ra is del Ra del Q1 plus del Ra del Q2 plus Fp plus F inertia on P dot del Rp del Q1 plus del Rp del Q2 del Q2 is equal to 0. Now we separate out the coefficients of del q1. So that is fa dot del ra del q1 plus f in a dot del ra del q1 plus fp dot del rp del q1. So let me move this a little left. So plus f in p dot del rp del q1 plus fa dot del ra del q2 plus f in a dot del ra del q2 plus this is fp dot del rp del q2 plus f in p dot del rp del q2 equal to 0. So del q1 and del q2 are arbitrary. That means it may so happen that we do not give any del q1 and we give del q2. So that is also possible because virtual displacements are arbitrary. So we may not give any del q1 and we give some del q2. Or in another way, we give one del q1 but do not give any del q2. That means if the sum has to be 0, then both these quantities inside the bracket should be 0. So this gives you two equations. So one equation is this is 0 and the other equation is this is 0. So one equation is this is 0 and the other equation is this is 0. So now you can actually write it in a tabular form. You can write it in a tabular form. So like this. So page, you can write it in a tabular form. So suppose you make a table like this. So this is for A and this is for P. So this is del R A del Q1 and this is, okay, write it like this. Del R A del Q1 and here del R P del Q1 to, this is the first row and this is the second row. So this is del R A del Q2 and this is the del R P del q2. So you can call this table of partial displacements. So let me call it table of partial displacements. And then here active forces, and the active forces are Fa and Fp. This is on A, this is on P. And then the inertia forces okay, I will just A and P. This is F in A is equal to minus M1 AA equal to, and this is F in P minus M AP. That means here what we have to do is we have to multiply this with this, this with this, this with this, and this with this to get the first equation. So first row, this term into this plus this term into this term into this plus this term into this plus this term into this plus this term into this. So this equal to 0. This gives you the first equation. Then this term into this term into this plus this term into this plus this term into this gives you the second equation. So see, Fa is the first term, Fa into del RA del Q1, this plus F in A del RA del Q1, so this into the first term, so this into this plus this Fp into del Rp del Q1 and F in inertia P into del Rp del Q1. So this equation and here this equation. So if you call it, suppose we call it F1, so we call it F1 and we call it F2 and we call it F inertia 1 and we call it F inertia 2, and here we call it PD first row first column, PD that is partial displacement first row second column, PD second row first column, PD second row second column. Then your equation will be then your equation will be f1 into dot pd 1 1, this is a vector, plus this pd is also a vector because this array is a vector. These are all vectors. So pd 1 1 plus f2 dot into pd 1 2 plus f in 1 dot pd 1 1 plus f in 2 dot pd 1 2 equal to 0. So this is equation 1, and then f1 dot pd 2 1, that is second row, plus f2 dot pd 2 2 plus f in 1 dot pd 2 1 plus f in 2 dot pd, these are also vectors, this is pd pd 2 2 equal to 0. So this is equation 1 and this is equation 2. So now you actually have to fill up the entries in this table. What are these quantities, what are these quantities, and what are these quantities. So once you fill up this, then you can form the equations. So let us see what are. So RA is Q1I. So del RA del Q1 is equal to I, and del RA del Q2 equal to 0. Similarly, or null vector rather. Similarly, RP is equal to Q1 I minus L sin Q2 I plus L cos Q2 J. So del RP del Q1 is again I, and del RP del Q2 is equal to minus L cos Q2 I minus L sin Q2 J. So see, we have got these 4 entries. So we have got these 4 entries. And now what is F1? F1 we already know, this is minus KQ1 I, and this is M2G J. So F1 and F2 we already know, and for this we need to find out the accelerations. So accelerations means we have to So RA equal to Q1 I RA double dot is equal to Q1 double dot I, and that is equal to AA. So we have easily got AA. And RP equal to this. So RP dot is equal to Q1 dot I minus L cos Q2 dot I minus L sin Q2 dot J, and RP double dot is equal to Q1 double dot I minus plus L cos Q2 L, this is sine, this is sine minus sine cos Q2, from cos Q2 we get minus sine Q2 dot, so Q2 dot square, and then minus L cos Q2 double dot I, and from the next term, so let's put minus L cos Q2 dot square minus L sin Q2 double dot G. So this is A, B. So now see, we have got all the terms in these three tables. So you can now fill up the tables. So let us take these tables. So this is I, this is I, so this is 0, del RA del Q2 is 0, and del RP del Q2 is minus L cos Q2I minus L J. So, and obviously the active forces are FA, FP, active forces are on A and on P. So this is minus K q1 I m2 g and inertia forces, these are the active forces, and the inertia forces minus m1 AA, and that is AA, you know, minus equal to minus m1 q1 double dot I. This is A, and minus m2 AP, and that is equal to minus m2 so I am writing S for sign to accommodate it in this small space, and C for cos. Yes. So now things are almost done. So this multiplied by this plus this multiplied by again this plus this multiplied by this, then this multiplied by this, this multiplied by this multiplied by this multiplied by this, and this multiplied by this gives you the first equation. And then you go to the second column. So this multiplied by this plus this multiplied by this plus this multiplied by this plus this multiplied by this gives you the second equation. That means this is PD 11 PD 11 multiplied by F1 plus PD 12 multiplied by F2 plus PD11 multiplied by F in 1 plus PD12 multiplied by F in 2 gives you equal to 0, gives you the first equation. Then we change the color. PD 21 multiplied by F1 PD 22 multiplied by F2 plus PD21 multiplied by F in 1 plus PD22 multiplied by F in 2 equal to 0 gives you the second equation. So now you can form the first equation and the second equation. So this is how you can systematically progress and systematically form the equations of motion from virtual work principle.